Good morning, everyone, and welcome to my presentation, the characterization of pharmaceutical formulations using broadband acoustic resonance dissolution spectroscopy. My name is Niamh O'Mahony. I'm a PhD researcher in University College Cork. First off, this morning, I would like to ask you a question. Is sound a credible or reliable method of testing pharmaceutical formulations in industry prior to their release to market? And I know what you're thinking. You're thinking, what is she talking about? How is that possible? But I propose an instrument to you today that can quantitatively analyze formulations using sound as the medium. The instrument I propose is Broadband Acoustic Resonance Dissolution Spectroscopy, or as BARDS, as we refer to it in the lab day today, and I'll be referring to it as BARDS throughout this presentation just to make that a little bit easier to digest. BARDS is a patented platform technology based on an acoustic phenomenon observed when adding a compound to a solvent. The principle behind the instrument is an acoustic phenomenon first described by A.B. Woods in 1930. The effect has been intermittently discussed in literature and was most notably characterized by Frank S. Crawford in a series of papers published during the 1980s, giving the phenomenon the title the hot chocolate effect. So what is the hot chocolate effect? It's a phenomenon of wave mechanisms first documented in 1980 and later published in 82, where the pitch heard from tapping a cup of hot liquid rises after the addition of a soluble powder, and in hot chocolate that would be sugar. It was first observed while making hot chocolate. BARDS is a complementary approach to surrogate testing. It's standard dissolution testing based, and the speed of real-time data acquisition and how the data can be extrapolated matches that of standard regulatory methods. A compound generates a unique acoustic profile at a fixed solvent volume and analyte concentration. The dissolution of an analyte introduces gases trapped between and within particles and reduces gas solubility in solution. This leads to the reproducible change of the compressibility of solution due to the outgassing effect, which acts to slow down the speed of sound. The sound is introduced using only a magnetic flower that taps the inner wall of the glass vessel gently. This mechanical energy then dissipates as sound energy resonates through the solution. The instrument can be seen in this image, and an interior view can be seen in figure 2b. I'm just going to go through each section of the interior just to show how this phenomenon is actually used in real life. So the system consists of a standard disposable wave boat that you have in any lab here, set on top of a tipper motor securely. So the sample is automatically introduced to solution after 30 seconds once a volume line resonance frequency has been established. The microphone records this change in frequency associated with the sample dissolving in the solution as the stir bar taps off the glass vessel. The magnet that stirs this stir bar is set off center to enable this tapping required for a BARDS spectrogram. So what is a BARDS spectrogram? What does it look like? So you can see here a typical raw spectrogram from the BARDS instrument. So the acoustic profile of interest is called the fundamental curve. So the F-min, or the frequency minima, represents an equilibrium between the rate of gas formation solution and the rate of gas equilibrium at the surface. In BARDS analysis, the fundamental curve is used to make comparisons between individual experiments. The volume line is recorded for the first 30 seconds to establish the resonance frequency of the glass vessel and its associated 25 mL of solvent, which is typically a weak acid, a weak base, or even just deionized water. Organic solvents are usually stepped away from. Once the sample is added, the resonance frequency decreases to the frequency minima, followed by a return to steady state, marking the full dissolution of our sample. So the spectrogram can be plotted in two different ways. So the first is as per the raw spectra, where you plot frequency against time. And a more quantitative way of analysing the data is through the gas volume in mils against time. So BARDS is a green, cost-effective and a time-efficient method of dissolution testing. And that's due to the ease of use, the low solvent volume requirements, and the short time frame required per run, which is an absolute max of 50 minutes. So BARDS applications are universal across the food and pharma industries, including screening of raw materials, quality control, inter and intra-batch analysis, blend uniformity, detection of counterfeits, and so many more across the industries. And this presentation is just going to illustrate a few of those pharmaceutical applications that I've been working on personally, which include the stability testing, characterization of enteric-coated microspheres, tablets, MUPS formulations, as well as effervescent, chewable and liquid formulations in a little bit less detail, simply because that is a currently evolving area of BARDS. So first off, what is a microsphere? So in simple terms, a microsphere is like a really tiny mini tablet, and they are in spherical form as opposed to your classical cuboidal or uh, cylindrical form, and they are typically coated in an enteric-coated polymer or functional polymer, and this has a protection angle to it. So enteric coating is used to protect the stomach, typically from the API, or the API from the stomach, and it dissolves in a specific media. And they're enclosed in a capsule, as you can see on my left. They're not that coloured in real life, they're usually just white, but they come in kind of coloured capsules as everyone is taken. And if you shake them and hold them to you, you can actually hear the microspheres move around in them. So this shows the analysis of functional polymer coated microspheres. So functional polymer coated microsphere means that it dissolves in your stomach. It is made to dissolve in acid. So in this case, these microspheres were analysed in 0.01 molar HCl. And they are functional polymer to taste mask, so you won't get any unpleasant aftertaste from this drug. So this figure 6, shows the profile of caffeine samples of various coating thicknesses of UV-Vis EPO, a functional taste masking polymer. The black profile represents BARDS data, while the red profile represents the UV-Vis data. Data shows that the coating polymer is behaving according to its desired purpose. The UV-Vis data shows the concentration of caffeine is close to 0 during this lag time phase. So what is the lag time phase? The lag time is the BARDS response to the polymer coating erosion, and it's represented in a BARDS spectrogram by this kind of flat line that you see here. And that's purely the outer coating, that functional polymer coating, eroding in the media provided. So once the coating is fully dissolved at the end of that lag time, there is a rapid increase in the concentration of caffeine. And this causes the end of our lag time and a decrease in the BARDS spectrogram. So the lag time increases as our coating load increases. So that's from A to C, the lag time length increases. So figure 6A to C demonstrates categorically the time-dependent release of the drug is related to the erosion of that UV-Vis polymer. This is followed by the disintegration of the core pellets, followed by a rapid dissolution and release of the drug from F-min onwards. These results demonstrate the integrity of the polymer coating during the lag time, and it's actually the only technique, BARDS is the only technique on the market that can actually detect the integrity and characterize the functional polymer or enteric polymer coatings under 10 microns. So we're going to look at a true enteric coating polymer now, and that is UV-Vis L30D55, and it's designed for ingestion in your intestine, therefore is tested in a basic media, so bypasses the stomach straight to your intestine. And we've chosen 0.0 molar NaOH for this analysis. So figure 7 shows also a stability analysis for an inter-batch comparison of samples obtained at similar time points during the enteric coated process. So samples were tested initially when received, and also tested 24 months later. So the interbatch variability in the initial analysis shown to be insignificant. However, after 24 months, a change in enteric coating dissolution and breakdown has occurred. Figure 7A shows the BARDS data for batch 1, B for batch 2, and C for batch 3. The dissolution behaviour remains similar to the previous analysis, with insignificant error to the dissolution. However, the lag time of all samples has increased in the last 24 months. A trend is observed whereby the thickest coating demonstrates the most considerable change of sample behaviour. Figure 7B shows the analysis of batch 2, and if you look to that navy profile, that end of spraying profile, you see it doesn't actually return to our steady state as it did in batch 1 and batch 3, and that's due to undissolved excipients in our solution remaining in the glass vessel once the run is complete, whereas this didn't happen for batch 1 and batch 3. They were clear colourless solutions at the end of the run. And just a point to note that you can see the F-min of our analysis is steadily increasing with the increased coating thickness. And the next type of formulation we're going to have a look at today is MUPS formulations. And then a basic way to describe these is there are these enteric-coated formulations that you've seen, these enteric-coated microspheres we've seen before, compressed into tablet form with some extra excipients to help with binding and coated in this pink layer. So they're more like a tablet, and they're a multi-unit pellet system. So figure 8 represents the data collected for the MUPS formulation of omeprazole branded Lorasec MUPS of 3 different dosages, so 10 milligram, 20 and 40 milligram. The samples were analysed in 0.01 molar NaOH as they're an enteric-coated polymer. And there's actually a 2-event dissolution taking place here. It's very different to ones we've seen previously. So the first event is that pink outer coating that encompasses those microspheres, erodes and releases the pellets coated in UV-Vis L30D55 into solution. And our second event, marked by that dashed line, It it relates to the erosion of that enteric layer and subsequent disintegration and deaggregation of the spheres. So the hydroxide actually perforates that outside coating and a hole appears in that pink coating. So there's actually a microsphere released from very early on, hence why we don't get a true lag time in this dissolution profile. So we go into enteric-coated tablets, same as our microspheres, just a bigger tablet size. And I'm going to present to you an EDDDI plot. So figure 9 shows an EDDDI plot for the Bluefish 20 milligram pantoprazole formulation dissolution. So BARDS is used to track the individual processes associated with dissolution. BARDS spectras of enteric-coated tablets and microspheres can be mapped using an erosion, disintegration, deaggregation, dissolution, and integrity plot. The red profile represents the UV-Vis analysis during the BARDS experiment. The UV-Vis profile measures the concentration of dissolved pantoprazole released from samples. The initial decrease in the fundamental curve is due to the entrained gas in the outer enteric tablet coating, followed by a subsequent return to the lag time during the erosion of the polymer. No pantoprazole is released during this lag time as demonstrated by the UV-Vis. Once the coating erodes and the inner tablet core disintegrates, there is an immediate release of that concentration of the API in solution, indicated by that downward slope to our F-min in the BARDS spectra. The end of the disintegration process is followed by the deaggregation of the tablet. And at that F-min, we actually have about 50% pantoprazole release, and that is indicated by our UV-Vis spectra. And then the frequency profile gradually returns to steady state in the BARDS spectrum during the deaggregation phase. So we're going to leave enteric coating behind now for a while, and we're going to have a look at effervescent tablets. So we all know about effervescent tablets. We've all had Barocca or seen effervescence in the supermarket, and they have a really simple method of action whereby you add the tablet to water, and the acidic and the basic components react with one another in water, producing CO2 and that characteristic fizz. So BARDS can actually be used to track that characteristic fizz. So 300 milligrams of tablets were samples analysed in both tablet and powder form. And this weight was selected for the resulting resonance frequency minimums to ensure it satisfied the Crawford equation. So if our frequency minimum goes below 1, it doesn't satisfy the Crawford equation and therefore is not BARDS compatible. And the tablets in this case are very large, they're 4 grams. So as you can imagine, the F-min is very low when you analyse the full tablets and causes a huge amount of oversaturation of our solution. So figure 10 shows a BARDS analysis of aspirin-containing effervescent formulations. Alka-Seltzer and Bayer aspirin are both marketed by Bayer and perform identically in solution. And then Disprin Direct and Disprin Extra are also from the same company and perform identically in solution. However, there's a difference in API content for both of these. They're all highly reproducible. The two Bayers, there's only 24 milligram difference in API, which is relatively insignificant. As you can see, they perform identically in tablet and powder form, whereas the Disprin formulations actually have a 200 milligram difference in API content. So it's interesting to see that there isn't an effect of that in our BARDS profile when it's such a specific and fingerprint-like technique of analysis. So our next type of formulation is actually chewables, and chewables are fantastic geriatric forms, especially because you don't have to swallow the tablet, you chew them into a paste and then ingest them. So we're just going to look at one form of this, which is Gaviscon, and it was analysed in 0.01 molar HCl. Samples were only analysed in tablet form as the powder were found not to be wettable in the aqueous solution. And just to note that extended time frame at 3,000 seconds, 50 minutes, as opposed to the kind of 600 seconds of a time frame we've seen previously. So both formulations are sugar-free and contain similar excipients. The difference in active ingredients is expected to contribute to the profile of these. And just to note, there's actually a bimodal dissolution of our Gaviscon Extra, where there's 2 plateaus. The first at the F-min for 400 seconds, and the second at the 750 second time point, and that lasts 500 seconds. And this is due to the tablet breakup process, whereby the tablet disintegrates and deaggregates twice. So what do I mean by that? How does it do that twice? So the formulation is actually a 2-component tablet. So it's bound as one, but there's a pink side and a cream side. And through observation, we actually found that the cream side breaks apart first and causes the initial equilibrium in the F-min. And then the pink side takes a little longer to dissolve and causes that second equilibrium during the deaggregation of the initial tablet dissolution. So that cream side's Deaggregation. The deaggregation of both tablet components in unison cause the analysis to be less reproducible, and then it doesn't fully return to steady state due to undissolved excipients in solution, due to that pink side, unlike the peppermint. And there's a difference in mass between these two samples, where there's 1.4 grams for the Gaviscon Extra and 0.8 grams for our Gaviscon Peppermint. Our last type of formulation is liquid, and we're going to look at suspensions, which have the API remaining in the liquid undissolved, and syrups, which are cough medicines. Typically, they are used as cough medications, and they have the API dissolved. On our left, we see the comparison of paracetamol containing formulations of different dosages, and they are 5 ml dosages, and the Panadol Baby and Infant have 120 milligrams in the 5 ml, and the Calpol 6 Plus is 250 milligrams. But they all perform relatively similar. It's interesting to note that the Baby Panadol performs almost identically to the Calpol 6 Plus, despite the difference in dosage. And you can see on our right, there's a smaller dosage in the Benylin for children of Argustafen, and Lemsip produces the most amount of gas. And there's an identical spectra, the chesty cough and phlegm from Benylin, as they're the exact same formulation with the same APIs, just marketed under different names. So first off, what has BARDS got to do with the industry, and what's it going to happen? So it's the potential to save money and be greener, and perhaps even become a regulatory policy and practices worldwide, as well as speed up the release to market of drugs, which would be an amazing thing to achieve during my studies. I hope I've answered the question that I posed at the start. I hope you think BARDS is a viable option. And I would just like to thank the NUI Awards, my supervisor, Dr. Darren Patrick, and UCC for the use of their research labs. Most importantly, to the Forge conference today. Thank you for giving me this fantastic opportunity to explain my research. It's been truly an enjoyable experience. And thank you all for listening. I really appreciate your time. Don't hesitate to contact me if you have any questions. Thank you.